I'm sorry we got cut off there. I need to finish the projection. If I want to call this the projection of A onto B, this shadow of A, then what do I need to do? I know that this side length is the length of the hypotenuse, length of A, times the cosine of this angle, so that this over this is cosine. I want this length to be hypotenuse cosine theta. Similarly, this would be hypotenuse sine theta, so that this over this is the sine of theta. That's true in any right triangle, right, from trigonometry. And now if I want this to be the projection of A onto B, then its length has to be this amount, plus or minus. Cosine could be negative, recall if theta's obtuse. Let's just consider the acute case, then this is the length. And then we want that to point in the direction of B. So we want to take it times the unit vector in the direction of B. We take B divided by its length. And so we take this length of the projection times this direction gives us this vector right here. So there's why we define the projection this way, because this can now be written by multiplying it top and bottom by length of B as length of B, A, length of B, cosine of the angle between them over length of B squared, B. Alright, so multiplies top and bottom by length of B, you get this, which is just A dot B over length of B squared B. We take B and we multiply it by this number to get the projection of A in the direction of B. There's the definition of the projection, so that we'll get this vector that we want. Now here's an application. Out of the note, suppose we want to take this vector, oops, next example. This vector A equals 1, 0, minus 2 and project it onto 2, 1, minus 1. We take A dot B, it's this times this plus this times this plus this times this is 4. Length of B squared is just the sum of the squares, right? The length of B is root sum squares, so length of B squared is sum of the squares. 2 squared plus 1 squared plus minus 1 squared is 6. We take A dot B divided by length of B squared and multiply by B. That's the projection definition, and we get 4/6 of 2, 1, minus 1 is this vector here. So there's how we can find a projection. This has all kinds of neat applications. One of them is with the direction cosines. Suppose I have a vector V in 3 space, and I want to find a unit vector in the direction of V. How can I find that? Well, one way is to divide V by its length. Another way is using the direction cosines. Also, these angles are obtuse themselves. What's the angle from a vector to the x-axis alpha? What's the angle to the y-axis beta? What's the angle to the z-axis gamma? We can compute it like this. This is an interesting application of projection. For a vector u of length 1, it turns out that the projection of any vector v onto u, well, we remember that it's v dot u over length of u squared times u. Well, length of u is 1, so it's just v dot u times u. So actually, the number that scales a unit vector to take a projection in its direction is just the dot product. When we want to project this vector onto the x-axis, this is how long it is. Now, we also have that v dot u is length of B, length of u, cosine of the angle between the two vectors. So if u is a unit vector, so if this is 1, we have that the cosine of the angle between v and a unit vector is just v dot u over the length of v. And that means, in particular, that when we project a vector on the x-axis, we can make u the unit vector I, and we can take cosine of alpha, the angle of the x-axis. We'll call these direction cosines. The cosine of alpha is v dot I, a unit vector, over length of v. And the cosine of the angle to the y-axis, we just take v dot j over length of v. And similarly, the cosine of the angle to the z-axis is v dot k over length of v. That gives us the cosine of the angle to the axis, and then we can take the arc cosines of these and find these three angles. So the fact that a unit vector dot product with another vector gives you the length of the vector times the cosine of the angle between them allows us to calculate these formulas for direction cosines. The cosine of the angle to the x-axis is a dot I over length of a, or you can just say it's the first component of a over length of a, a1 over length of a. Cosine of beta is just the second component over length of a, and cosine of the third component is the third component. Cosine of the third angle is the third component over length of a. So here's a simple example here. For this vector 2, 1, minus 4, its length is square root 21, so you take its first component divided by its length. That's the cosine of the angle of the x-axis. You take the arc cosine, you get 64 degrees. You take the second component of the vector divided by its length. You get the cosine of the second angle, arc cosine is 77 degrees. Third component of the length of the vectors, arc cosine is 151 degrees. Those are the three angles of the axes. And what's more, we have this nice theorem that comes up occasionally. The three direction cosines form a unit vector in the direction of v. You can take, or a. You can take the length of a times this unit vector and recover the vector. So this is a theorem. Oops. Length squared of this is 1, and therefore the length of this is also 1. Well, finally, the last application here is to work. One thing I don't like about your book is that it gradually extends work. I wish they just wait and give it all at once, but I think in physics class you need some of this earlier, is why they do this early in the book. But we'll follow that because that's what the book does. Work in physics or engineering done by a force in one dimension, recall, is just force times displacement. It can be negative if I hold a weight over my head all day, but it slips down. I've actually done negative work, gravity doing positive work against me. So it's not like our usual concept of work. If I hold a weight there all day, I feel pretty tired. I feel like I did a lot of work, but I did zero because I didn't move it, right? Force times displacement. Now, work in two dimensions, or higher, so I'll say in n dimensions, is not going to be force times displacement, but force dot displacement. Multiplication is actually the dot product in one dimension, it turns out, so this is a special case of this. It's the same definition, just extended to more dimensions. In one dimension it's force times displacement, but in more dimensions it's force vector dot displacement vector. In other words, if I take a force vector here, and I move an object here, work is force dot displacement. I should have boxed it here, I suppose. Why would that be? Here's the reason. What we want to do is say, well, this force can be broken into components, a perpendicular component and a parallel component, right? We can rate it as the sum of this vector plus this vector. We're only going to count the work done by the force where it actually moves it. So if it moves it in this direction, we're only going to count the component force in this direction. But this component of force, remember if this is the angle theta, is length of force, cosine of the angle. So that's the force pointing in the direction it actually displaces. Following this prescription, force times displacement, we want to say that the work is the length of the force, the cosine of the angle, times the length of this one, the length of displacement. Oh, but that's just the dot product. So we generalize work to more dimensions. We'll say work is the component of force in the direction the thing moves times the displacement is force dot displacement. Here's a simple example. Kind of a classic one. A child is pulling a wagon. Let's say with the handle at 30 degrees from horizontal. Suppose this child pulls with a force of 10 newtons. Oops. So that'll be the magnitude of the force. And maybe the child pulls the wagon 10 meters. That's the displacement. How much work does the child do? Well, what's the force vector here? If the force is 10 newtons long, and it's an angle of 30 degrees, then we can break this up into components and say this side is square root 3 over 2 times the hypotenuse, or 5 square root 3 units long. This one is 1/2 the hypotenuse, is 5 units long, right? It's the 30, 60, 90 triangle, so this is 1/2 the hypotenuse, this is square root 3 over 2 times the hypotenuse. And now the work is force dot displacement, but the force is 5 square root 3 in the x direction, 5 in the y direction. That's dotted with the vector here, 10 meters in the x direction, 0 in the y direction. And we get 5 square root 3 times 10 for 50 square root 3 newtons meters. Alright, force times distance is the units. That's clumsy to write all the time. People write this instead joules, J. So 50 square root 3 joules is the work done by the child to pull the wagon 10 meters, pulling at an angle of 30 degrees with a 10 Newton force. Try the homework problems, and next time we'll do a lecture on cross product.